So on Monday, we introduced the second quantization for single particle quantum mechanics, and we derived such a equivalent expression for single particle potential energy, potential operator, and we intentionally insert this unit matrix or identity matrix on the left and right side of this operator V. And the purpose of doing this is to actually rewrite this operator in terms of a creation and destruction operator. Okay, so as you can see here, that this identity matrix is encircled by a red circle, but if we look at this yellow part of this matrix element, and we could see that this is a number. Okay, so suppose V operator is a matrix and it is sandwiched by the Dirac-Broglie on the left and Castet on the right. And after this operation, this is nothing but a number. Okay, so this number is called this matrix element of V operator. But apart from this matrix element, there's a Dirac-Castet on the left and Broglie on the right. So since this is just a number, we could just move this number around and we place it any place we want. Suppose that we simply just move this coefficient in front and we put together the remaining operators and we group together this kind of combination of this Dirac-Castet and Broglie, and you immediately notice that this is not a number but a matrix, because last time we mentioned that Dirac-Castet is n by 1 column matrix and Broglie is 1 by n row matrix. Therefore, the direct product of these two matrices gives you n by n, which is a matrix and which is not a number, and therefore this is the quantum mechanical operator, which I call this A alpha prime alpha double prime wearing a hat. When I put this hat on top of this A, what I mean this is an operator. Okay, so the operator wears a hat, but the number doesn't. But this A operator, defined this way, has a physical interpretation in quantum mechanics, namely this operator destroys a castet, say alpha double prime, but create another state called alpha prime. So the proof of this interpretation is here. Suppose I operate this A operator onto any other arbitrary state called alpha, and what I get is the following result. And this operation results in this alpha prime state if alpha is the same as alpha double prime, but 0 otherwise. So you can see immediately that the non-trivial result comes from the fact that when alpha equals to alpha double prime, which means that this operator destroys this alpha double prime, but to create alpha prime, because at the end of the day, the result is actually alpha prime. So alpha double prime state is gone. Okay, so this operator has a physical interpretation to destroy an alpha double prime, but create alpha prime. Okay, so whenever there's non-trivial states, say alpha double prime, or alpha prime, this means that we have a particle in that state, right? So if there's no particle, and we denote this state as empty state or vacuum state. So the vacuum state is actually a normalized state. So I can rewrite this A operator, and in a slightly different way, namely I insert this kind of a vacuum normalization factor here. So if you look at this stuff, this is nothing but 1. But if I just intentionally insert this 0, 0 normalized state, and in between this alpha prime, alpha double prime state, and I could actually officially define a creation and destruction operator in the following sense. So for the yellow stuff here, it's actually an alpha prime state. It's a castet on the left, and the empty state or vacuum state is a Broglie on the right. Okay, so remember, we interpret this A operator as destroy Broglie on the right and create a castet on the left, right? And so we can interpret this yellow stuff in the same way that we destroy a vacuum state, okay, and we create alpha prime state. So what do I mean by destroy the vacuum state and create a single particle state? Well, this is the same as we create a particle out of nothing. So it says that we create a particle out of vacuum. So namely, we literally create a particle. In the same way, we can interpret this orange stuff in the same way that we destroy an alpha double prime state and then we create empty state. What do I mean by that? Well, again, so if I destroy this alpha double prime state, which means that there was a state called alpha double prime state, which I destroyed, and then I create an empty state. Okay, so which means that there was literally a particle there, and I killed this particle. I destroyed this particle, and after this operation, the original particle state is gone. And instead, I created nothing. I create empty state, which means that there's no particle in the final state. So therefore, the original single particle state is destroyed by this operator. Is that clear? Okay, so conventionally, we use a dagger to indicate that we create a particle, and non-dagger is a notation for destruction operator. Therefore, I could simply just rewrite this in terms of C dagger alpha prime, C alpha double prime. Of course, the C dagger and C are quantum mechanical operators, so officially they should wear hats, but for the convenience, and I can remove these hats. But when I write this A operator in this fashion, what I mean is that C dagger creates a particle in state alpha prime, and C alpha double prime destroys the particle which was originally in state alpha double prime. Okay, so nothing is strange and mysterious. We just rewrite this quantum mechanical operator in the Dirac notation, and we could interpret this operator as the creation and destruction of a quantum particle state. So you can read the first few chapters of Flansburgh, which contains a similar but slightly different notations to define this creation and destruction operator. So this is just a potential V, which describes the scattering of a single particle by this potential operator V. Okay, but what about the kinetic energy? Let's second quantize the kinetic energy for a single particle. And you know very well that the quantum mechanics tells you that the kinetic energy operator for a single particle is P hat squared divided by 2m. So this P operator in quantum mechanics is nothing but this minus h bar, the partial derivative of this wave function with respect to x, right? So this is from quantum mechanics. But now let's play the same trick for this kinetic energy operator. Again, I could rewrite this in terms of this identity matrix. Right, so we could still use this eigen state basis alpha and alpha double prime, alpha triple, alpha prime state to rewrite this kinetic energy operator. So let me just do this. And since we already derived this A operator, so I simply just use what we have derived over here. The A operator is simply just C dagger C. And in the same way, we could rewrite this kinetic energy operator in terms of a C dagger C, right? And multiply by this matrix element. And we could define this C dagger alpha prime as the alpha prime and vacuum state, and C alpha double prime is this. Okay, so this alpha prime, alpha double prime labels the eigenstates of, in some space. It's just a label of the quantum state. Some quantum states labeled by some quantum number. So you could consider this alpha as any kind of states, quantum states that you learn from quantum mechanics. Suppose that this alpha state is the eigenstate of momentum operator. So in quantum mechanics, you know that this momentum operator, when it operates on this momentum state, gives you this momentum as eigenvalue multiplied by the momentum state, right? Suppose this alpha state is just the eigenstate of a momentum operator, which satisfies this eigenvalue equation for momentum operator. Then we could very easily simplify this matrix element. So this matrix element is nothing but P alpha square and alpha P alpha prime and P alpha double prime, right? So you simply just use this eigenvalue equation and plug in here, and you get this. So this eigenvalue P alpha double prime square multiplied by this inner product between the P alpha prime state and the P alpha double prime state. But this is nothing but delta function, right? Okay, because this eigenstate for momentum operator satisfies this orthonormal condition. So they are orthogonal to each other if the eigenvalue, say P alpha prime, is not the same as P alpha double prime, so this vanishes. And if they are the same, this gives you 1. And you plug in this kind of eigenvalue and back in here, what you get is nothing but what? 1 over 2n sum over alpha and P alpha square C delta alpha C alpha. Since alpha prime equals alpha double prime, it doesn't matter whether I choose this notation to be alpha prime or alpha double prime, since the alpha is a dummy variable. So this is the final result for the kinetic energy operator, which says that you sum over this kinetic energy eigenvalue and labeled by this alpha prime, where alpha prime is the eigenstate of the momentum operator, and you multiply this kinetic energy in state alpha prime by this C delta C operator. But what is C delta C? You will see later that this is nothing but a number operator. So this is the number operator, which counts the particle number, and this says that the total kinetic energy is the summation over all different, say, eigenstates of momentum operator, and inside the summation, you multiply the kinetic energy of a particle at state alpha or alpha prime, and multiply the number of that particle. In other words, this tells you that this is the sum over the kinetic energy per particle in state alpha and multiply by the number of particles in alpha. Right? So this is the meaning of kinetic energy. If there is an eigenstate of momentum operator, which is labeled by alpha, and you simply just count how many particles in alpha state and use this number and to multiply by kinetic energy in that state. Is the same spirit when we calculate the expression value of a quantum mechanical operator, or you throw a dice. So what is the expression value when you throw a dice? When you throw the dice could give you 6 different results, right? 1 and 2, 3, 4, 5, 6, right? And the expression value of this when you throw a dice is the number 1, okay, value 1 times the probability to get 1, right? Plus 2 times the probability that you get 2, and plus 3 times the probability to get 3, plus 4 times the probability to get 4, plus 5 times the probability to get 5, plus 6 times the probability to get 6, right? From the high school mathematics. Okay, this is the same thing here. So suppose we have many different states which are eigenstates of momentum operator. So the expression value of the the kinetic energy is nothing but the kinetic energy when you stay in state alpha 1 times the probability that you get the alpha 1 state, and so on and so forth. So this number operator, C delta C, tells you the probability that you get the particle stay in this alpha state. So the total kinetic energy is the sum over the kinetic energy per particle in the general state alpha times the probability to get the particle in that state. Right? Good. But the purpose of doing this is actually to get the number operator out of this single particle kinetic energy operator, because the number operator is the most important object that we should take advantage, because we can count the particle number when we express all this quantum mechanical operator in terms of the number operator. Okay, so we haven't shown that this C dagger C really has this interpretation of the number particle operator, but we will show that this operator really count the particle number. Okay, so it's called number operator. Okay, so we can define the second quantization of a single particle potential operator and also the kinetic energy operator. So we can combine these two pieces to define the full Hamiltonian for a single particle quantum mechanics, but in the second quantized formulation. And later we will generalize the single particle representation to many particle system, and we should distinguish between the fermions and from the bosons, and we will introduce similar notation like this, but in many fermion, many boson system. Okay, so let's take a short break. When we come back, we will generalize this to many particle system. Okay, so here comes your slightly non-trivial homework. So we already defined this single particle potential operator V, and so now we can link this sort of a matrix element or some kind of a expression value of a V operator and to the Schrödinger picture. So in the ordinary quantum mechanics, you learn that when you evaluate the expression value of a quantum mechanical operator, what you will do is you simply just calculate this quantity that you put the wave function psi alpha star on the left and psi alpha on the right, and you sandwich this potential operator, right? And then you sum over all possible state alpha and alpha prime. But here you could show that this is nothing but you actually perform such a calculation that you evaluate this this expression value and of V operator sandwiched by this position operator R. And remember that in Schrödinger representation, the Schrödinger wave function is nothing but the projection of your quantum state psi onto the position operator. So we will come back to this, a relationship between the second quantized operator and the first quantized, Schrödinger representation of the quantum mechanical operator. So there is a direct one-to-one correspondence between the first quantization and the second quantization formulation, and this is just the first exercise that you could review your first quantization knowledge in quantum mechanics, and you should use that Dirac notation, and you could derive this identity over there. So let's talk about this many particle system and the second quantization of a many particle. Before that, we should review the first quantization. Before we talk about this second quantization, but we should review the first quantization in many particle systems that we already learned from quantum mechanics. So suppose we have many particles and they are described by some kind of a real space Schrödinger wave functions, right? So this is psi Ri. Okay, suppose we can solve the Schrödinger equation for many particle systems, and we know their wave functions as their eigenstate, eigen wave functions, psi of Ri. Then we know everything. So naively, we will need to have this many particle wave functions. So which is a function of all this position vector. So there's a particle number 1 in this position vector R1 and so on and so forth. There are n particles, and they are described by a collection of many particle wave functions, which are made of a product of a single particle Schrödinger equation. So, and we need to know the probability distribution over space. And we could use that probability distribution to calculate any expression value of all observables. But as we already mentioned, that this is a mission possible because we cannot solve that many Schrodinger equation for that many particles exactly. So, but suppose we know this wave function, and we should take care of their quantum statistics. Namely, when we exchange the particle, we should respect this, Fermi-Dirac and Bose-Einstein, statistics. Namely, this lambda can take, say, plus or minus 1. Plus 1 for bosons and minus 1 for fermions. So that's just some basics. But we can construct the many-body wave function. Suppose we know solutions to the Schrodinger equation for that many particles, and we could form orthogonal and normalized orthonormal basis for a single particle. Okay, suppose this is just a orthogonal and normalized eigenbasis for a single particle in state nu, and we could form a many-body wave functions like this. Any arbitrary many-body wave function is actually a linear combination of all the product of the single particle wave functions like this. So this is just a generalization of a two-body problem that the total wave function of a two-particle system is actually the product of two single particle wave functions, right? And you should respect the Pauli principle for fermions and total symmetric wave function for bosons. Okay, so any arbitrary many-particle wave functions, total wave functions, many-body wave functions, could be constructed by linear superposition of the product of all single particle, wave functions with appropriate coefficients. Okay, you could make a linear combination of all possible, product states of a single particle wave function, and you can form an arbitrary total many-body wave function. Suppose we know the answer to the Schrodinger equations. In order to respect the quantum statistics, we should distinguish between these fermions from the bosons. So the quantum statistics will put a constraint on this coefficient. So in other words, we need to make the symmetrized or anti-symmetrized wave function of the product state, which is the kind of determinant. Okay, so we need to symmetrize or anti-symmetrize the product of the single particle wave function when we make the linear combination of this product. Okay, to respect this quantum statistics, namely for bosons. So this is a plus for fermions. This is minus. So the plus and minus, index here refers to the fact that when we, calculate this determinant, there's many terms, right? Plus or minus something. Okay. So the plus sign refers to the fact that all these different terms, inside this, when we evaluate determinant, should be plus, but the minus refers to the fact that this is actually the anti-symmetrized product. So the product, the plus sign refers to, symmetrize. There's all this n different terms when you make this product, okay? And the minus refers to the anti-symmetrized, and which means that this is just a determinant. Okay, so we should take care of this quantum statistics, and as a result, now this more accurate way of writing down this most general total many-body wave functions in terms of the linear combination of the product states is given by this. So I use different coefficient B to represent this expansion coefficients, and we need to symmetrize or anti-symmetrize this product of a single particle state. So in other words, we first need to symmetrize or anti-symmetrize the product of the n single particle wave functions, and then depending on this symmetrize or anti-symmetrize, we could actually attach the coefficient in front of this product so that you compose any arbitrary many-body total wave functions. Okay, so this is the way that we construct many-body wave functions. Suppose we know the solutions to the Schrödinger equation to all these millions and millions of particles, and this is a way, what I mentioned previously, that we follow the particle. Okay, so this is the method that we follow the particle, meaning we trace the real space wave function for each of the quantum particle, and we solve the Schrödinger equation for all the single particle set, and we follow the particle in real space. Okay? As I mentioned previously, that this approach fails because it is not possible to get solutions to that many single particle states when we solve this millions and millions Schrödinger equations. But still, naively, if we have the solutions and we could follow the particles, and when we follow the particle, we know everything we need to know. But the problem is that in practice, it is not possible to follow all the particles because we don't know the solutions for this many particle Schrödinger equations. But there's an equivalent way. Instead of following the particle, we can count the particle number. So when we count the particle number, we will change the basis that we express in many particle wave functions to occupation number basis instead of the real space Schrödinger basis. But it is an equivalent way to express the many particle wave functions, not by following the particles, but by counting the particle number. Okay, so let's take a short break. When we come back, we will start to introduce alternative way. Instead of tracing the particle in real space, what we can do is to count the particle number in a different basis called occupation number basis. This is just review of quantum mechanics in many particle systems, where in general you could describe any arbitrary many particle wave function in terms of a single particle wave functions by symmetrizing or anti-symmetrizing the single particle product wave function. Okay, but this kind of explanation leads to a dead end. Okay, so let's continue. So I mentioned, to follow the particles, we need to solve the Schrödinger equation for millions and millions of particles, which is not possible. But instead, we should find another approach to actually more efficiently get information of this quasi-particles, and that approach is called count the particle number, and this is the way that the second quantization approach is taken. So we, instead of following the particles in real space, which is not possible, and we will try to use an equivalent way but different approach, namely we actually listed all the possible states in this many-body system, labeled by this quantum number nu1, nu2, up to nu n. And then we count how many particles that populate on each of these possible quantum states, nu1, nu2, up to nun. Suppose we define the basis states, so-called occupation number basis. Namely, we listed all the numbers, which is the population or occupation number for each of the quantum states in the many-body system, right? And then we count them one by one, okay? So I should use this basis as my new basis to count the particle number. And when you sum over all this occupation and nu j, you get a total number reproduced. Okay, so it doesn't matter how you describe the system, either by following the particles or by counting the particle number in specific quantum states, at the end of the day, you could do either way, right? So they are equivalent, okay? So maybe I could label this, wave function R1 particles, that this particle could actually occupy, any of these quantum states, and there's another particle in R2 which may, occupy another different quantum states, and so on and so forth. So we don't know where they are, but we do know what quantum states they are living. So it's like you exchange the way that you find a particle. You can find a particle by tracing their real space wave functions, but I don't do that because I cannot solve the Schrödinger equation. Instead, I know all the possible quantum states. I simply need to count how many particles in that state and how many in this state and so on and so forth. When I exhaust all this particle in my systems up to capital N, that many particles, and if I know all this occupation and all this, eigenstates, and I know everything. Okay, so I don't need to follow particles, but I can simply just count the particle number. If I can construct such a occupation number basis, which is also normal basis, again, so because all different particle number states are orthogonal to each other. For example, if I have two particles, so I could have 0, 2, or 1, 1, or 2, 0. So if there are only two particles and there are just two possible states, I can just simply label all the possible states of those particles by the occupations. Okay, so there are three possible two-particle wave functions. One is, no particle occupying nu1 state, but two particles occupy nu2, and the 1 state is that one in nu1 and another one is nu2, and the 2 states is two particles occupy nu1, but no particle occupy nu2. So if I know all these occupations, and I know how to describe this two-particle system, right? So I can generalize this to 3-particle, 4-particle, up to infinite number of particles, as long as I know all this occupation number. But we need to define the occupation number operator, NUJ, wearing a hat, which gives you this occupation number as the eigenvalue, and multiplied by this NUJ state. Okay, so we need to define properly the NUJ operator, which counts the particle number from this eigenvalue equation, right? But we already found this when we define this creation and destruction operator. Remember, the C dagger nu, C nu represent the number operator, but we haven't proved that. We will prove this. Okay? So, in other words, we need to construct a Hamiltonian which is expressed in terms of this number operator or occupation number operator. Then we know how to count this particle by this simple eigenvalue equations. Okay, so therefore the problem is reduced to define this properly, this occupation number operator. Suppose we know and we have a way to define this number operator, then the remaining problem is really simple and straightforward, because for fermion bosons, these occupations can be slightly different. Okay, so for fermions, the occupation can only be 0 or 1 because, for any fixed quantum states, there's only at most one fermions occupy the same states. There's no double occupancy of the fermions of the same quantum states, and that is, restricted by the Pauli principle. But of course, you could have 0 occupation in this fermionic state. However, for bosons, you can have all kinds of particle number from 0, 1, 2, 3 until infinity, because there's no limitation for bosonic particles to stay in any quantum states. So you have infinite number of possible occupations for bosonic system. So if I use a cartoon picture to illustrate the Hilbert space of this fermionic and bosonic system, as illustrated here, that you could very easily see the great advantage of using this language. Okay, so there's a saying that in physics or in any science problems, when you find the efficient language and you find the answer. If you do not find the correct language, and the answer will not pop up. But if you can actually simplify the problems by using the efficient language, then the answer is straightforward. And this is the case. So for fermions, the Hilbert space consists of only occupation 0 state and occupation 1 state, right? Nothing more. So for each of the states, you have no occupation for fermions, or one single occupancy for fermions. And as I mentioned, we can define the creation and destruction operator for fermions and also for bosons. Suppose we know this occupation number basis. To go to the empty states from the single occupied states, we can simply just apply this destruction operator. So destruction operator, when you act on this single particle states, gives you empty state, okay, with a proper coefficient, which we will address in just a moment. And then if you would like to go to the basement, but from the empty states, it's not possible because there is no underground floor anymore if you are already in this empty states, because the zero particle state is the ground floor. So if you keep lowering the particle number from the ground state or zero particle states, you get nothing. So likewise, I can go upstairs. If I start from this empty states with no particles, and I want to go to the first floor where there's a single particle, single fermions, and I can simply just apply this creation operator. So the creation operator, when it acts on this empty states, will give you the single particle states multiplied by some coefficient. But again, there's no two particle states in fermions, so if I keep climbing upstairs, there's no second floor. So if I keep increasing the fermion number from 1, and there's no occupation 2 state. Okay, there's no such a thing. Okay, so for fermions, it's really simple that you only have 2 floors, the ground floor or the first floor. Okay, you could go upstairs or downstairs by applying this creation destruction operator. And you can go anywhere you like. Good. For bosons, again, we have infinite number of floors, and you could climb ladders upwards or downwards. Upwards, if you start from this zero boson states, and you could apply this B dagger, you get to the first floor, and then apply another B dagger, you get the second floor, and so on and so forth. But once you are at the ground floor, you cannot go to the basement. But you can go to the infinite number of particle states for bosons. Okay, so this is just a cartoon picture, but we will come back to this when we defined the many-body fermion operators and boson operators. Let's just start define this many-particle creation destruction operator for fermions. Before that, let me just summarize this correspondence between two different ways of treating this many-body wave functions. Suppose we count the particle number, and we already defined the occupation number basis. Then for arbitrary many-particle wave functions, and it can be constructed by linear combination, linear superposition of all the basis states in occupation number basis with the proper coefficient A. But again, this is alternative way with respect to the following particle. As we just mentioned previously, that if we follow the particle and we know this single particle Schrödinger wave functions for millions of particles, then we could simply just symmetrize and anti-symmetrize of this product of a single particle Schrödinger wave functions, and then we multiply this by a prefactor. We sum over all possible states, and this is another way to actually describe many-body wave functions. So the important statement is that these two different approaches are equivalent descriptions of a many-body wave functions. Okay, so at the end of the day, even if we don't know where the particles are, but if we can count the particle number and their corresponding states, and we could equally well describe this many-body wave functions. Okay, so the first quantization says that we need to follow the particles, but it's not possible. But then we could try an alternative approach, which is this occupation number basis. Okay, but these two different descriptions are entirely equivalent, although we don't know the solution for this first quantization approach, but we do argue that as long as we could count the particle number, we could equally well describe the same thing. So let's just try to define these operators. As I mentioned that there are different occupation number for this occupation number basis, then we could use this notation. So I don't bother writing down all these different numbers for the occupation, but I simply just use the collection of all those different numbers and nu, and this represents all this nu1 up to nu(n), the states, and this should form this orthogonal normalized basis, and the vacuum is a state where there's no particles. And again, this potential term in this many-body system could actually be expressed in terms of a similar fashion that we already defined for a single particle. Okay, so namely we could define properly the single particle creation destruction operator out of a many-body system. Okay, so this is what we will do. Okay, so let's take a short break. When we come back, we will officially define the fermionic creation and destruction operator in a many-particle system. So please read the first two chapters in Flansburgh, where you can find all these definitions of occupation number basis and also the creation destruction operator for fermions and bosons. So let me just start introducing this fermionic destruction operator, or sometimes we call this annihilation operator. Okay, so the official definition to destroy or annihilate a fermion or electron is defined here that, again, we have, say, two Dirac states. One is the cat state on the left and Bragg state on the right. So you destroy the states, the Bragg state on the right, and you create a state on the left, right? So this is nothing but you destroy an initial state and you create a final state. Okay, so the initial and the final state are labeled by all their occupations. Here, this is a fermion, so there are only two options, 0 or 1, right? So suppose I would like to destroy an electron in state P. What I do is that I write down this initial states with all this occupation number, and in particular, I'm interested in the state P. Okay, there was electrons here initially, which means that the MP is actually 1. Okay, so this is my initial state. So if I want to destroy that state, I would like to write this initial state this way. And what about the final state? Well, final state is a state where MP is 0. Okay, so by the same way that we interpret the C dagger and C operator in a single particle system, we define the CP operator as a destruction operator the same way that we destroy an initial state and we create a final state. Okay, so initial state has a particle, and the final state for the P state has no particle. Okay, so we destroy the single particle state at P, and we create a no particle state at P, right? And therefore, we officially destroy a single fermion in state P. Okay, but of course, we need to take care of this, the so-called anti-commutation relations for fermions, and the way that we take care of this, anti-commutation is guaranteed by this prefactor -1 to the power of MP, where MP is the sum of all this occupation from, say, 1 to actually P minus 1. Okay, so let me just write it here. So this is N P minus 1, and this is N1. Okay, so there is P minus 1 states on the left of this MP state, and we need to sum over all this occupation to the left of this MP state. And we define this number as capital MP, which is the number of the times that you need to exchange these two fermion wave functions. And therefore, this represents the number of times we need to exchange two fermion wave functions, which means that this is the number of times you should add the extra -1. Multiply this -1. The number of times we need to multiply -1. So let me illustrate the logic behind this definition. As you may know that this MP minus 1 and MP and MP plus 1 up to NN. So suppose I write this many-body state in the occupation number basis like this. So what I mean is that we have, suppose this is psi 1, and this is psi P minus 1, and this is psi P plus 1, psi N. Okay, so suppose the occupation for fermions, there are only two options, right? 0, 1. Okay, so if I use this N1 here, N1 could be 0, 1. So suppose N1 is actually 1. Then I have a particle, right, in state 1. And I could use the wave function, Schrödinger wave function, to describe such a particle in state 1. But if N1 is 0, and I have nothing, and again, I could simply just write down all these possible single particle wave functions, and this collection of all this occupation is actually describing such a product of all these possible wave functions of single particle. Okay, suppose there are all particles occupying all the states, and I have n such a wave function, right? Multiply together, right? Okay, so but of course they are all fermions, right? So this is fermions. So let me just illustrate the logic behind this -1 to the power of MP. So where does it come from? Okay, so this kind of a -1 to some power comes from the fact that when we use this operator C to actually operate on this any states, what we do is actually we need to move around all these operators and the wave functions until we actually reach that state. So let me just show you this operation. So suppose I try to destroy a single particle state P in its many-body wave function or many-body states labeled by all these occupations. So I should focus on the states MP, right? But what is this, the collection of all the occupation? This is nothing but the product of all these possible wave functions from this N1 to actually to all the N, right? Okay, so which means that I need to operate this collection of all these possible wave functions. Okay, but remember that when we write down this occupation, this ordered, if I translate into this product of all these many single particle wave functions in the product, which I mean is that, psi 1, follow these orders should be written on the very left, and psi 2 is just right next to psi 1, but to the right, and so on and so forth. So we need to follow this order of this occupation when we write down this single particle wave function like this. Okay? But this operator Cp will actually affect only this wave function here. Right? So it doesn't destroy all the other states, but only destroy the state P, which means that we need to really move this operator to the next nearest the left of this psi P. So namely, this operator Cp doesn't affect all the other single particle wave functions, but only affect this psi P. So what we should do is actually we need to actually move this operator all the way to the left of the psi P. Or in other words, we need to actually move this psi P all the way to the left, to the right of the Cp operator. So which means that we should move this until we really reach this psi P, just right side of the Cp operator, and all the other single particle wave functions are not affected. Right? Okay, so, and this is the way that we perform this operation, that the Cp operator really destroy this single particle state at state P. Okay, but in order to do this operation, perform such operation, we need to move around all this single particle wave functions all the way to the right of this operator. But when I do so, remember, if there are fermions, when we actually move this psi P from the right to the left side of psi P minus 1, both states are occupied by single electrons, then we should multiply a factor minus 1, right? And so on and so forth. So if all the states before state P are all occupied, then I should multiply a bunch of minus 1 factor all the way to the left of psi 1. But if there's no particles populate on some of the states, then I don't need to multiply this minus 1. But how many times that we need to multiply this minus 1? Well, this is precisely this capital N tells us. This capital N tells us that you need to sum over all this occupation, right? So from N1 to N, P minus 1, N1 plus N2 plus blah, 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 plus N P minus 1. If all these N occupations are 1, so this is actually P minus 1, right? But if some of this N is 0 or 0, then you simply just put 0 here. Therefore, this number, which is the sum of all the occupation before the state P, represents the number of permutations or exchange that you need to do before the C operator acting on this psi P. Right? Because there are fermions, so once you move around this, this single fermion wave functions, and you should multiply by minus 1 factor. And this capital MP simply just trace how many times that you need to perform these permutations and exchange of two fermion wave functions, and this actually keeps track of all these minus 1 factors. So you can actually check this definition. Just a moment, we could actually check whether this kind of definition satisfies this Pauli exclusion principle. This also leads to so-called the anti-commutation relations. Okay, so let me just erase this part and I leave this here, and we should, go on to describe these properties of those destruction operators acting on this occupation number states. So the properties of CP are the following. If there is no states, no particles in state P, and if I deliberately would like to destroy these empty states, and as I mentioned, there's no underground floor, there's no basement for fermions, so this will be 0. And if I destroy a single particle state P, I get empty states at P multiplied by -1 to the power of MP. Okay? And if I destroyed twice of any states, give me 0. Okay, so this is the properties of a CP destruction operator for a single fermion, and we could use this definition to check the anti-commutation relations. So in ordinary quantum mechanics, you know that if you exchange these two fermions wave functions, you get -1, right? But this relation is encoded in this definition over here that you could show in the second quantized representation of this operator. You can show that this is still the same thing. So C dagger I, C dagger J, anti-commutator 0. Or non-dagger is the same thing. Namely, if I use this combination, the CI-CJ plus CJ-CI as my operator, and I should act this, operator onto any occupation number states, then this will give me 0. Okay, if I follow the definition of the CP. So let's just check this. Okay, so we could check that this definition satisfies this Pauli principle. Suppose the CP and CP prime acting on this MP is 1, MP prime is 1. So what I do is actually I use the definition over there. First, I need to destroy the state P prime. Okay, but I need to actually count the number of occupation right before MP prime, right? So -1 to the power of what? MP prime and M1 MP equals 1, MP prime -1, and MP prime is 0, right? Okay, so suppose that P prime stays lives on the right side of the P state. Okay, so the first operation is that we need to destroy the state P1 particle, which has the 1 particle here. Then after this destruction operation, so we have 0 particles staying in this P prime state, and multiplied by this prefactor -1 to the power of MP prime, where MP prime is defined as somewhere over J -1 and J, right? Good. So now let's just perform the second operation. So the second operation tells us that we need to destroy the state MP, but we need to keep track of this occupation right before state P. So this is another factor, MP. So let me finish this. So you will get the final state is that there's no particle state in the p and p prime, but you need to multiply this vector, right? Minus 1 to the power of np prime times minus 1 to the power of np. So you can show that if I reverse the order of cp prime, namely if I do the opposite, so let me just use this, cp prime, cp acting on the same state, you will get minus 1 times cp prime acting on the same state. Okay, so we don't have time to finish this check, but we will do that next week. You can show that if I reverse the order of this successive two destruction operations, and you will get the same states, except now there's an extra minus sign in front. Okay, and therefore if you add this two, move this line to the left of this equation, then you get this statement that this cp prime plus cp prime cp, when you act this operator onto any states, gives you 0. Okay, so this kind of anti-commutation relations actually followed this kind of a Pauli principle for these two electron wave functions. Okay, so you can generalize this anti-commutation relations to many particle systems. If I define the CP operator like that, then this kind of anti-commutation relations are automatically satisfied. Okay, so perhaps that's enough for today. And next time, we will again illustrate how this creation-destruction operator of the fermions in many particle systems, how these actual calculations go, and the relation to the Schrödinger pictures of the first quantization. Okay, so I recommend that you should read this corresponding chapters in Flansburgh, like chapter 1 to chapter 2, for details. Okay, so this is the beginning of advanced solid-state physics. Namely, we should define such a destruction and creation operator, and then we can count this quasi-particle number, and we will derive this full Hamiltonian in the generalized solid-state systems, and use this occupation number operator to rewrite this Hamiltonian, and then we can solve this problem in the low temperature limit. So I stop here, and if you have questions, please let me know.